All right. In this video, I'm going to overview the procedure sections for Lab 4. In Section A, you're going to measure the distance to two objects on Earth using either a protractor with a string or your phone's compass app. In Section B, which has 3 parts, you're going to observe, identify, and measure the distance to a main belt asteroid using Earth baseline parallax. In Section C, you're going to measure the distance to Venus, again using Earth baseline parallax, and then you're going to use that measurement to determine how big the Sun-Earth distance is, how big the astronomical unit is. And then in Section D, you're going to measure the distance to Alpha Centauri, the closest star system to our own, using the astronomical unit, which you just measured, and stellar parallax. Okay, let's begin with Section A. In this section, you're going to measure distances as surveyors do. But first, you have to pick a location. If you're in an on-campus section, your instructor will pick the location for you. At the University of North Carolina at Chapel Hill, we use a very straight wall on a south-facing observation deck. It doesn't matter that the deck is south-facing, but it's important that the wall is very straight. Your instructor will pick 2 objects for you to measure the distance to, and these objects should be directly across from the wall, perpendicular to the wall. We use a smokestack on the next building over as our nearby object, and the campus water tower, which is even farther away, as our second object. Now, if you're taking this lab online, you'll need to find your own location. Again, you need a straight wall and 2 objects pretty much straight across from it. Some students do this indoors. In fact, if you're doing this yourself at home, you'll want to do it on a smaller scale because you will need to check the distances you measure with parallax by also measuring these distances with a tape measure. And that can be difficult to do if your objects are too far away. Okay, next, we're going to begin our measurements. Now, if you're doing this on campus, you should use a protractor, and the protractor should be provided by your instructor. It's the same protractor that we use in the Globe and Lights version of Lab 2. It comes with the hole pre-drilled at the 0, spot through which you can tie a string, and then you can use the string to measure angles on the protractor, as you see in this figure here. Now, if you're at home, you probably don't have one of these protractors, but what you can use is the compass app on your phone. It comes pre-installed on most phones. It's not as accurate as the protractor, but it should be good enough, particularly if the distances you're measuring are not too far away. Now, to carry out the measurement, begin by going to the left-hand side of the wall. If you're using the protractor, line the back of the protractor up flush against the back of the wall, as you see in this diagram here. Again, it's very important that you have a straight wall with a straight back edge that you can line the protractor up against. Then lower your eyes to just above the protractor and line the string up such that it's pointed at your object. Then, without moving the string, raise your head and look down at the protractor and measure the angle off the top of the protractor and estimate it to the nearest tenth of 1 degree. If you're using your phone's compass app, you don't need to worry about lining it up against the back of the wall. Just point it to the object you're trying to measure the distance to and measure the degrees off of the phone. Once you've done that, record that angle here, then mark your position on the wall, maybe by leaving a pebble, and walk to the right-hand side of the wall and repeat your measurement and put that angle here. Then you'll take the absolute value of the difference between these angles. In other words, the positive value of the difference between them. You'll record that here. That's your angular shift. Next, you need to measure the baseline, the distance between your two observing points. For this, you can use a tape measure, though you may have to use it multiple times if it's not long enough, or you can use a yardstick, end over end over end. Once you've measured the baseline, which I want you to do in feet, enter that here, and then you can use the parallax equation discussed in the background sections to calculate the distance to the object. You enter your baseline here in feet, and your angular shift here in degrees, and this will be the distance to the object that you've calculated using parallax. Now, if you're at the University of North Carolina at Chapel Hill, you're measuring the distance to that smokestack on the building immediately across from the observing deck, and the true distance to that smokestack is 360 feet. If you're at a different institution on campus, you'll be measuring the distance to a different object, and your instructor will provide that distance for you. And if you're at home, you're going to have to measure the true distance yourself, again using a tape measure or a yardstick, end over end over end. Once you have that true distance, enter it here and calculate your percent error, which goes here. Then you're going to repeat this process for the object that's farther away. You'll measure your first angle and put that here, and your second angle and put that here, and then you can calculate the angular shift between them, which you'll put here. You'll measure the baseline, the distance between your two observing points, and put that here, and then using the angular shift and the baseline, you'll calculate the distance to your object using the parallax equation and put that here. Then you'll need the true distance to your object. And if you're at the University of North Carolina at Chapel Hill, it's 2,800 feet to the water tower. If you're at a different institution, the distance to your second object, your more distant object, will be provided by your instructor. And if you're at home, you'll need to measure the distance to your second object yourself. Again, using your tape measure or a yardstick, end over end over end. And that goes here. Finally, you can calculate another percent error, and that goes here. You'll discuss your sources of error here, and then we'll ask you a series of questions. Which of your measurements was less accurate? Which should have been less accurate? For a fixed baseline, at what point does parallax cease to be an accurate technique for measuring distance? And don't just say 10 kiloparsecs. That's as far out as the parallax technique currently works for astronomical observations. But that's not what we're asking. We're asking, what is the limiting factor? For example, in your measurement for a fixed baseline. And lastly, what are two ways that you could more accurately measure the distance to an object using parallax? Okay, let's move on to our astronomical observations. In section B, you're going to measure the distance to an asteroid in the main asteroid belt. In part 1, you learn how to select that asteroid and how to carry out this observation. This is described in this tutorial here. It's a difficult observation to make because you have to observe the asteroid simultaneously from both the northern and southern hemispheres. This requires special permission, which we can't give to everybody, but we will give it to your instructor, who can put this observation in for the entire class. And these data should be ready by the time you begin Lab 4. In Part 2, you'll identify which object in your images is the asteroid. And you'll do this by comparing one of your images to an archival image from the Digitized Sky Survey, or DSS. Now, you learned how to do this in Lab 1, and here is the tutorial on this from Lab 1, or you can watch this tutorial, which is specific to this lab. Once you've done this, you'll open one of your images and the corresponding archival DSS image in Afterglow. You mark stars that are common in both images, and you'll mark and label the asteroid in your image. Then you'll download both of these images as JPEG files on your computer and upload them into WebAssign here and here. Then in Part 3, you'll measure the distance to the asteroid. You'll do this by taking two images, one from the telescope in the southern hemisphere and one from the telescope in the northern hemisphere, that were acquired at either exactly the same time or nearly the same time. You'll align these two images and then stack them, which means average them together. How to do this is described in this tutorial here. And once you've done this, you'll download your stacked image as a JPEG file onto your computer and upload it to WebAssign here. Now, in the stacked image, the asteroid should appear twice, with a very small angular shift between its two positions. And this angular shift is due to parallax from observing the asteroid from two different vantage points, one in the southern hemisphere and one in the northern hemisphere. You'll want to measure this angular shift in Afterglow using the ruler tool and enter that value in arc seconds here. Next, you'll want to figure out the baseline between your two observing points. And that will be some fraction of the Earth's diameter. In the southern hemisphere, you observe the asteroid using one of our telescopes at Cerro Tololo Inter-American Observatory. In the northern hemisphere, you observed it using one of these telescopes. Which telescope you used, you can figure out by looking at the image info, and then you know what fraction of Earth's diameter is between our two observing points. You'll want to enter that fraction there, and then all you need to know is Earth's full diameter in kilometers. Now, you measured this at the end of Lab 2, and I want you to enter the value that you measured here. And then I want you to enter the true value here. We're going to use the true value to determine the baseline because we don't want the errors to accumulate from lab to lab as we work our way up the cosmic distance ladder. So the baseline is given by the fraction of Earth's diameter from here multiplied by Earth's true diameter from here, and you can enter the result here. Then you can calculate the distance to the asteroid using the parallax equation. The baseline goes here, and the angular shift, which you measured above in Afterglow, goes here, but be sure to convert it to degrees first. Then you'll have the distance to the main belt asteroid measured in kilometers because your baseline was measured in kilometers. And you can enter that here. Now, main belt asteroids are typically between 10 to the 8 and 10 to the 9 kilometers from Earth. Given this, is your measurement reasonable? You can enter that here and also discuss sources of error in this box. Okay, in the next section, section C, we're going to go through a similar exercise measuring the distance to Venus, but we're doing this for a particular reason, and that is to determine the size of the astronomical unit, which we'll need to carry out stellar parallax in the next section. So first, a little bit of background. Venus orbits the Sun once every 0.62 years. Given this, we can use Kepler's third law to figure out how far it typically is from the Sun. You do this, and you find that it's about 0.73 AU from the Sun. Now, Earth is at 1 AU from the Sun by definition. So when Venus is as close to Earth as it can possibly get, it's at 1 minus 0.73, which is equal to 0.27 AU from us. So if we could measure the distance to Venus at closest approach using parallax, we would know how many kilometers are in 0.27 AU. And consequently, we could figure out how many kilometers are in 1 astronomical unit. The problem is, Venus is very, very hard to observe when it's at closest approach because it's right in front of the Sun and we can't see anything. So instead, we've collected data when Venus was in this phase, which is a gibbous phase, and it's only in this phase when it's at this position in its orbit. You can do a little bit of geometry, and this position in Venus's orbit corresponds to a distance of 1.34 AU from us. So what we're going to do instead is measure the distance to Venus when it's 1.34 AU away. We're going to measure it using parallax. We'll get that distance in kilometers, and then we'll know how many kilometers are in 1.34 AU. And again, we can calculate then how many kilometers are in 1 astronomical unit. Now, the reason we've collected this data for you, instead of having you take another observation of Venus, is to do this measurement, we're going to need to image Venus simultaneously from different parts of the Earth in the southern hemisphere and again in the northern hemisphere. And we are going to need to align those images and stack them. But to align images, we need background stars. And this is where the problem arises. Venus is so bright that if we image long enough to see the background stars, Venus saturates and we can't carry out our measurement. If we image Venus short enough that it does not saturate in our image, we don't have any background stars to use to align the images. Now, our solution to this problem was to use custom filters, special pieces of glass that block most of the light in the center of the image, but let most of the light through in the outskirts. We deployed these in the southern and northern hemispheres, collected the data that you'll be using in this lab, and these custom filters are no longer on the telescopes. You can access the data in Afterglow's sample directory under Astro 101 Lab, Lab for Parallax, Venus. Then the analysis is just as in the previous section. You will align and stack the two simultaneously acquired images of Venus. and you'll measure the angular shift of Venus in the stacked image using the measurement tool in Afterglow. You'll upload your stacked image here. You'll input the angular shift in arc seconds here. You'll enter the fraction of Earth's diameter between the two observing points here and calculate the baseline using the true diameter of Earth. And then you'll calculate the distance to Venus when it's in this position, 1.34 AU away from us, using the parallax equation. Your baseline goes here. Your angular shift, once you convert to degrees, goes here. And you calculate the distance in kilometers, and it goes here. Again, that is 1.34 AU. So 1 AU is going to be that distance in kilometers divided by 1.34. You can enter that here. And then we give you the true value. The astronomical unit, its true value is 1.5 times 10 to the 8 kilometers. So you can calculate a percent error, which goes here, and you discuss significant sources of error here. Now in the last section, we're going to use the astronomical unit and stellar parallax to measure the distance to Alpha Centauri, the closest star system to our own. Alpha Centauri consists of two stars, A and B, and they are both very bright. So we will again use these custom filters that block most of the light in the center of the image, but let most of the light through in the outskirts so we can align our images. And since this is stellar parallax, these images are taken 6 months apart, one on one side of Earth's orbit and one on the other side of Earth's orbit. You can find these images in Afterglow's sample directory under Astro 101 Lab, Lab for Parallax, Alpha Centauri. Then the analysis proceeds just as before, as with the main belt asteroid and as with Venus. You'll use Afterglow to align and stack your two images and to measure the angular shift of the object in your stacked image. Now, with Alpha Centauri, since it's a binary system, you have two objects that you can work with. We recommend that you use the fainter of the two stars, Alpha Centauri B, to measure the angular shift. Once you're done, you can upload the stacked image into WebAssign here, and you can record your angular shift in arc seconds here. Next, we need the baseline between the two observing points. And since this is stellar parallax, these observations were taken on opposite sides of Earth's orbit. So the first question is how many AU, how many astronomical units across the diameter of Earth's orbit, not the radius, but the diameter. That goes here. And then I want you to convert that number into kilometers, first using your measurement of how many kilometers are in an astronomical unit, and then using the true value, both of which are in the previous section. We'll then calculate the distance to Alpha Centauri using the parallax equation. For the baseline, I want you to use this one that you calculated using the true value for the astronomical unit, so our errors don't multiply as we continue to work our way up the cosmic distance ladder. And then you enter the angular shift here once you've converted it to degrees, and you'll get the distance to Alpha Centauri in kilometers. You enter that here, look up the true value in kilometers and enter that here, calculate a percent error, and then discuss significant sources of error. Okay, that's it for this overview video.